This is the Auxiliary Water Supply System training video.
This video is designed to train inspectors on AWSS installations and inspections.
This is the AWSS team with the San Francisco Public Works. I'm Chris.
I'm Leia.
And I'm Nicole. Today we are going to learn all about the AWSS. In part 1, we will look at the history and how the system came to be. In part 2, we will learn where the water is stored for the AWSS. In part 3, we will go over different safety requirements when installing a high-pressure water system. In part 4, we will go over the equipment needed to install AWSS. In part 5, we will learn about the various materials that make up AWSS lines. In part 6, we will talk about the required appurtenances to assemble the materials. In part 7, we will distinguish between qualified, competent, and certified personnel. In part 8, we will discuss the site-specific work plan to be submitted by the contractor. In part 9, we will go over excavation and shoring requirements. In part 10, we will learn how the system is installed. In part 11, we will see the procedures to pressure test an AWSS line. In part 12, we will learn how to inspect the installation of a concrete vault. And in part 13, we will look at final acceptance.
In this part of the video, we're going to learn of the single cause of San Francisco's historical auxiliary water supply system.
The 1906 San Francisco earthquake struck the coast of Northern California at 5:12 a.m. on April 18 with an estimated magnitude of 7.8. 90% of the total damage was caused by the fires that occurred after the earthquake.
Within 3 days, over 30 fires caused by ruptured gas mains destroyed approximately 25,000 buildings on 490 city blocks. The map shown here shows the limits of the destruction.
As a result, about 3,000 people died and over 80% of the city of San Francisco was destroyed. The events are remembered as one of the worst and deadliest natural disasters in the history of the United States.
As a result of this disaster, the city of San Francisco decided to build the auxiliary water supply system. The auxiliary water supply system in San Francisco is a high-pressure water supply network built for emergency purposes. The system was first installed in 1913 with 77 miles of AWSS pipe. Now, a lot of the system requires replacement, and San Francisco plans on expanding the existing systems to reach more of the city.
The map shows the existing AWSS lines. As you can see, most of it is concentrated in the downtown area where all the high-rises are located.
The auxiliary water supply system is a gravity system that consists of high-pressure water mains and hydrants, a storage reservoir, tanks, emergency saltwater pump stations, fireboats, and cisterns. Water is stored in the Twin Peaks Reservoir, Ashbury Tank, and the Jones Street Tank. The color of the hydrant tops represent the location of the hydrant in one of the 3 distribution zones, as you can see here on the diagram. Notice the different elevations of the reservoir and the tanks.
With 77 miles of pipe, there must be large places to store all that water. In the next part, we're going to explore the reservoir.
The Twin Peaks Reservoir acts as the backbone of the AWSS and is located in San Francisco's Twin Peaks Hilltop. It is made up of a 10.5 million gallon storage reservoir.
In the event of an emergency, electricity most likely would not be running. For this reason, the Twin Peaks Reservoir sits at an elevation of 758 feet. The difference in elevation helps the reservoir to pressurize the black-colored hydrants in San Francisco without the use of electricity.
The Ashbury Tank has a direct connection to the Twin Peaks Reservoir and has a total capacity of 500,000 U.S. gallons. The Ashbury tank sits at an elevation of 494 feet and powers all the red-colored hydrants. The Jones Street tank has a direct connection to the Ashbury tank and has a total capacity of 750,000 US gallons.
The Jones Street tank has an elevation of 369 feet and powers all the blue-colored hydrants. Additional sources of water include cisterns and seawater.
Cisterns are underground water storage tanks used for emergency purposes. Each one holds about 75,000 to 200,000 gallons, and there are approximately 177 located throughout San Francisco.
There are currently 3 fireboats named the Guardian, the Phoenix, and St. Francis. They are located at Pier 22 and a half and can supply bay water to the city's east side waterfront via 5 manifolds. The fireboats supply salt water into the system only at times of emergency because the salt water may corrode the system. There is only 1 boat on duty at a time. When they're not in use, they are docked at Pier 23 and a half. Take one final look at this diagram again. At the bottom left, we can see pump stations number 1 and pump stations number 2, along with the fireboats that can introduce salt water into the system after the fresh water runs out. Pump station number 1 is located at the San Francisco Fire Department headquarters, located on 698 2nd Street in San Francisco. The second pump station is located near Fort Mason at 3455 Van Ness Avenue. AWSS work typically involves high pressure. It is important to take the correct safety precautions and not enter the trench while the line is fully pressurized. It is the responsibility of the employer to post recognized hazards that can cause or are likely to cause death or serious physical harm to employees. If connections break free, high pressure lines can quickly become struck by hazards. Pipe movement, separation, and whipping are all serious hazards at high pressures. The employer's health and safety plans should detail the dangers of working around AWSS high-pressure lines.
As always, it is important to wear the proper PPEs. The 4 PPEs that are always required are your hard hat, safety glasses, steel toe boots, and Class 2 safety vest. If loud noises are present, hearing protection is required. If dust is present, a dust mask is required. Welders require more protective gear such as fire-resistant gloves, clothing and boots, and a welding mask. When making lead joints, the qualified person must wear protective gloves, clothing, and a respirator.
Proper welding PPE includes a welding helmet that automatically adjusts to the flash filter, hearing protection, cap goggles, flame-proof clothing including long sleeves, gloves, apron, chaps, and last but not least, steel-capped boots. In addition, OSHA has set regulatory standards for basic welding and fire safety. If you would like to know the full details, go to standard number 1910, chapter 252.
When working around an open flame, especially with welding, never forget about fire safety.
At the most basic level, you want to inspect the welding area. Is it inside? Is it outside? You want to remove all the fire hazards, install all necessary guards. Welding or cutting must not take place unless all the hazards removed or guards installed. The contractor must have a hot work permit before starting operations and have a fire watch person stay 1/2 hour after operation ceases.
AWSS work is constructed in the public right-of-way, impacting pedestrians, traffic, transit, and buses. For this reason, a traffic control plan is needed.
For traffic safety, make sure the contractor has submitted a traffic control plan and is approved by SFMTA. Make sure the contractor selects appropriate sized equipment to lift the pipe. This 18-inch diameter pipe comes in 20-foot segments and has an average weight of 1,680 pounds. Another type of equipment you may see is a loader, which is ideal for unloading pipe off the truck. Next, we will see the type of equipment associated with welding. Here we see the welder setup with a boom truck and a pipe supported by pipe stands. The boom truck provides additional support in case the pipe stands tip over.
The equipment needed especially for AWSS installation includes welding equipment such as the torch and the tent to protect the welds from moisture. And when making lead joints, crucibles are needed to heat the lead.
A flamethrower is also used to remove excess moisture prior to welds.
Let's take a look at the different components of AWSS work. Here you can see a picture of the ductile iron pipe. The pipe has two different ends called the bell and spigot. The spigot end is marked by two lines and the bell end is wider. When connected, the spigot end is inserted into the bell end.
As you can see, the manufacturers from US Pipe and Foundry make ductile iron pipe in all sizes. At the largest size of 64-inch diameter, comes in 20-foot segments and has an average weight of 12,000 pounds. Next, we're going to look at components that are associated with changes in directions, such as elbows, T's, and gate valves.
AWSS components are highly specialized and come from a sole source contract with Olympic Foundry. At the time of this photo, materials came from Canada. Today, they come from Olympic Foundry in Seattle.
Here we see a 22.5-degree elbow.
Elbows also come in 11 and a quarter, 45 degrees, and 90 degrees bend.
They are made at Olympic Foundry.
Notice different components will have different connection types. The connection at the end here has ears. You see the ears, that means a mechanical joint is to follow. We explain the mechanical joint further in the film, but for now, our purpose is to introduce you to the different types of materials.
This is a T used to install laterals for the hydrants.
In this picture, we can see a hydrant assembly connected to a 90-degree bend via a flanged connection. The component at the bottom of the hydrant assembly is called a berry. Above the flange connection, we can see an unpainted hydrant assembly.
If the hydrant is reused, they shall be sandblasted, hosed down with water, and painted with primer with 3 coats.
The operating nut height has strict requirements and is noted at 20 inches plus 3/4 of an inch or minus ½ inch tolerances above the finished sidewall grade. The hydrant assembly should be installed plumb and maintain a 5-foot radius in circumference. This means that objects such as street poles and light poles should not be within a 5-foot radius of the AWSS hydrant. And here we can see a gate valve. The gate valve has a max pressure of 450 psi working pressure and a hydrostatic pressure of 900 psi. A wrench is used to turn the operator nut shown at the top of the gate valve. This opens or closes the flow of water. In this picture, we can see a flanged pipe spool, and it's basically a piece of pipe with 2 flanges on either end. Here we can see an air valve. The purpose of the air valve is to release air through high points in the pipe. The 3 components from bottom to top are number 1, the thread-elet, number 2, the pipe, and number 3, the 300-pound brass angle valve. The brass angle valve is used to control the flow of air. The ½ inch hole at the bottom is drilled in to install later by welding a thread-elet The spacing of these air valves really depends on the engineers or the design of the system. They typically occur on high points in the system or closed off by different segments by a gate valve. The purpose of this picture is to demonstrate which is a mechanical joint and which is a flange connection. At the bottom of the floor, we see the mechanical joint connection, and going into the gate valve, we see a flange connection. We will explain the mechanical joint connections in detail later in this video, but for now, if you can imagine those ears, those are the indicators for mechanical joint. Here we can see a bucket of stop bars. Please note the diagram to the right showing the stop bars in red. We will see the purpose of these stop bars later in the video. They are related to mechanical joints and will be welded onto the spigot end of the pipe. It is the responsibility of the contractor to furnish all fittings and castings for the AWSS work. Here we can see a stop collar. When you hear stop collar, you should automatically think mechanical joint. The stop collar should have OFCO, meaning it was made from Olympic Foundry. Take a look at the diagram to the top right of your screen. Notice how the stop bars are preventing the stop collars from falling off the spigot end of the pipe.
Here is a picture of an all thread. It is basically a giant bolt. Its sole purpose is to restrict horizontal movement of the stop collar. Note that the mechanical joint allows for some vertical deflection, aka pipe settlement. Here is a picture of a square plate washer. Its purpose is to distribute the pressure evenly around the stop collar, reducing the chance that it will loosen. Here is a picture of a nut which holds and tightens the square plate washer and all-thread assembly. The stainless steel wire binders are used to hold the all-threads in place.
The wire binders are twisted to tighten the configuration and prevent the all threads from popping out of the ears.
One of the appurtenances to AWSS work is pipe wrap. As you can see from the photo, the pipe wrap has 3 layers that help to prevent corrosion. The pipe wrap works by trapping corrosion-causing bacteria in the pipe wrap and not letting it live. Here we can see the workers installing the pipe wrap. A special type of pipe wrap tape is used to seal off the pipe wrap. This ensures that corrosion-causing bacteria does not get into the pipe wrap. Field lock gaskets are used in pressurized ductile iron pipes to prevent the joints of the line from separating due to thrust forces. Field lock gaskets have vulcanized stainless steel locking mechanisms that grip the pipe to prevent joint separation. They are designed to meet operating pressures of up to 350 psi. As you can see from the diagram, the field lock gasket goes in between the spigot and the bell. The field lock gasket locks into place as it grips the pipe spigot. Other appurtenances include half-inch crushed rock for the pipe bedding. A half-inch pea gravel is used as pipe bedding so as not to scratch the ductile iron pipe. This is important because the flange connections have minimum deflection that is allowed. All welders employed by the contractor to do welding on ductile iron pipe shall be certified welders experienced in the type of welding required. All workers who do welding work or do welding inspection must be certified through a certified testing facility. The American Welding Society has an international list of accredited test facilities. After the test applicant passes the certified inspection test, they get a certificate that looks like this. This is the certificate for QC1 for welding inspectors. Those who wish to become certified welders must pass the certified welder requirements as noted in QC7 standards. A qualified person pours a molten lead to create the lead joint for AWSS work. Another type of work that needs certification is plumbing. To do work on AWSS, laborers must be competent and under the supervision of a certified plumber. Here is the certificate for a grade D2 plumber, which is required for AWSS work. The contract documents will call out what types of materials will be needed. Check the submittals for what has been approved by the engineer.
Make sure the contractor obtains the necessary permits for the specific site. Permits may include excavation permits issued by BSM, special traffic permits from SFMTA, and night noise permits from BSM.
Due to utility conflicts, this vault has special requirements, and the schedule for the rebar must be followed as per plan. Each worksite has potential variations, and it is important to take in the environmental factors and other details that may affect how the work will proceed.
Make sure the trench dimensions have been sized to fit the vault dimensions per plan.
Here we see they're about to install 18-inch ductile iron pipe for the AWSS work. Before the excavation begins, the contractor should have an approved shoring plan. The shoring plan should include a minimum pressure for the whalers. In this case, it's 38 KSI. Details such as the lagging and the whalers are very important, so be sure the contractor follows the specified shoring plan. One of the main concerns from an inspector standpoint is safety. Here we see the boom truck supporting the pipe in case it tips over. In addition, the pipe is supported by pipe stands, which gives the welder 360 degrees access to the pipe. Per SFPW specifications, the welding rod shall be NIROD 55 or Xiron 224 or approved equal. The welding rods are typically held in a heated container and taken out before use.
Here, the certified welders are welding the stop bars onto the spigot end of an 18-inch DIP. The stop bars hold the stop collar in place once it has been mechanically jointed.
When inspecting the weld, make sure there is a continuous weld and no slag. Slag is when there's air pockets or bubbles which weaken the weld. If slag is found, have the welder reheat it and redo the weld.
A flamethrower is used to eliminate any excess moistures before re-welding the stop bar.
With extreme heat, the weld may cause the mortar on the inside of the pipe to flake or pop off. If this happens, reject the pipe.
A successful weld will completely fuse the collar stop to the pipe.
The welder strikes the stop bar 3 times with a 22-ounce hammer. If the weld fails, it must be corrected.
Here we have an existing cast iron pipe where we need to install a lead joint to attach a new cast iron fitting from Olympic Foundry. So in order to make the lead joint, you need to first install some oakum into where the bell and spigot end meet. You can see the contractor here stuffing oakum into the joint to start forming the mold for the lead.
Here we see the contractor wrapping the rope around where the new lead joint connection is to be made. The workers secure the rope flush against the cast iron pipe and the mechanical joint adapter. It's important to note that the contractor should tie the rope tightly against the existing cast iron pipe in order to form a mold for the new lead joint. A heat-resistant putty is used to make sure the molten hot lead does not drip through the pipe.
To create a seal, the contractors put putty around the rope.
They form a funnel with the putty to then pour the molten lead in to make the joint.
The funnel made out of putty is now shaped up and ready for the molten hot lead.
A crucible is used to hold the lead and is connected to a propane tank burner.
It's always good to have a fire extinguisher on hand when melting the lead.
Inspection tip: clear any trench obstructions before lowering molten hot lead into the trench. Here you see the qualified person pouring molten hot lead into the mold that you previously saw made with the oakum, rope, and putty.
In this part of the video, we're going to go over pipe laying. As an inspector, we want to make sure that the entry point of the pipe is big enough and that the spacing between the shores can fit the pipe.
If the pipe hits one of the struts, this can cause a cave-in. There's typically 1 or 2 laborers at the bottom of the trench that must intercept the pipe as it enters the trench.
In the earlier part of the video, we saw the collar stops being welded onto the ductile iron pipe. Here, in this part of the video, we can see the spigot end of the ductile iron pipe being inserted into the cast iron bell. This connection is called the bell and spigot. As an inspector, you want to make sure that all connections are made tight to the touch and that the correct bolts and pieces of equipment are being used. Here we can see the contractor connecting the gland to the bell end of the connection. The purpose of the gland is to seal in the rubber gasket to form a watertight seal.
With any mechanical joints, the contractor must gradually tighten the bolts in a cross pattern as you can see here.
In the next step, the workers will install the all threads, the square plate washers, and the hex nuts against the collar.
Once they've connected the all threads, washers, and nuts, you then secure the mechanical joint using stainless steel wire binders.
And this is what the final mechanical joint should look like.
The main difference between a flange connection and a mechanical joint is that a mechanical joint allows deflection. A flanged connection is rigid. Now that we know what a mechanical joint is, let's transition into thrust blocks.
A thrust block is a concrete form that provides end restraint to minimize movement in AWSS pipe. The AWSS lines are prone to movement due to the high pressure water, especially when the lines change directions.
Thrust blocks typically occur at 22.5, 45, and 90-degree bends at hydrant tees in the pipe.
It is important that the thrust block is poured against undisturbed soil.
Take a close look at this picture. If you look closely to the left, you can see that this thrust block has been poured up against disturbed soil. That is because a utility was there previously.
When there is no place for the thrust block on the outside of a bend, It can be poured on the inside of the bend with ties around the pipe, securing it into the thrust block.
Next AWSS component we will talk about is the installation of the gate valve.
This is an existing cast iron gate valve to be removed and replaced with a ductile iron gate valve.
And now we see the new gate valve being installed. The dismantling joint, as shown in blue, gives workers access to the gate valve in case of mechanical failure. For flange connections, the number of bolts and the bolt pattern will differ with different pipe sizes. In this part of the video, I'll show you how a flange connection is made. This gate valve has a flange connection, and you take two flanged pieces, insert a gasket in between them, and bolt them off. The number of bolts will differ with different pipe sizes, but it's important that they are bolted in tightly. As seen before, the bolts here must be bolted in a cross pattern. As you can see from the chart, connections are allowed some amount of deflection based on the pipe size. Settlement reference monitoring points are set up by the engineer in key spots. In this section of the video, we will go over the pressure test.
The contractor must submit as-built drawings to the city representative at least 24 hours prior to the hydrostatic pressure test. The CM must submit the pressure test request form to the water department, specifying the new location of the AWSS pipe. This must be requested at least 72 hours in advance of the test.
It is the responsibility of the contractor to coordinate 10 days prior to the pressure test with the SF water department.
For new AWSS lines, it is important to pre-soak the line for 16 hours at line pressure, which is about 90 to 150 psi. After the line pressure is soaked, contractor may move into the AWSS pressure test.
The pressure test works with a fire truck using its internal pumps to send pressure through the water line. The fire truck sits upstream into the pipe segment in question, and downstream for the pipe segment is capped off with either a plug or a valve. The test works by sending pressure downstream into the pipes while the pipe is capped off. This allows the pressure to build and simulate actual pressure once the line is turned over and accepted.
The green fire truck is a retired fire truck, which is now owned by the water department and used for testing. The pressure test must hold at 350 psi for 30 minutes. As you can see, the current pressure in this test is at 310 psi and is ramping up to 350.
At the discretion of the water inspector, the pressure is ramped up in 50 psi increments to the final pressure of 350 psi. Let's take a look at what happens when the contractor fails the pressure test. Further downstream, we see the contractor has failed the first pressure test. The line did not hold at 350 psi for 30 minutes. Evidence of visible water is signs that the contractor has failed the pressure test. Here we can see the contractor working to retighten the bolts along the dismantling joint. They suspect the leak is from the piece in blue. The workers aim to retighten the bolts along the dismantling joint, so in the next retest for the pressure test, they will have no visible leakage.
All joints must be exposed during the pressure test to check for leakage.
It is important from a safety aspect to evacuate the trench once the high pressure test goes on due to safety concerns for pipe bursts or pieces coming out. Here is the contractor's second attempt for the pressure test. After ramping up in 50 psi increments to the final pressure of 350 psi, the contractor has held this pressure for 30 minutes and has passed the pressure test.
This is the AWSS pipe test form that the inspector is required to fill out with the test results and must obtain signatures from PUC.
With the pressure test out of the way, it's time to build the AWSS vault. The vault's main purpose is to protect the gate valve from traffic from up above or movements in the ground. The gate valve is all important to shut off a line in case of any kind of leak.
Here the contractor lays out the materials to make sure they're ready to build the vault.
Before the concrete pour, check that the contractor has the correct concrete mix. The contractor sets dobies below the rebar so that it achieves sufficient cover.
Here you see the contractor taping off the vault sump to protect it from the concrete pour.
It is important that the contractor uses a concrete vibrator when pouring any concrete with rebar so that there is no air voids in the concrete so that it can hold on to the rebar. The contractor must follow the rebar schedule. A pipe sleeve is inserted to separate the walls of the vault from the pipe.
This is the frame for the vault lid.
Here the contractor is setting the frame for the lid.
With the frame of the lid set, the contractors pour concrete into the walls of the vault.
Here they installed the rebar cage for the top of the vault with the casting for the lid.
The 4 hooks for the lid of the vault, as shown here, are taped off to preserve them. The hooks can be used to remove the lid in cases of emergency. The contractor seals off the pipe from the vault wall with mortar. The contractor fills any voids with non-shrink grout, as shown here. The vibrator is all important when it comes to pouring concrete with rebar. The contractors use a straight edge to level out the excess concrete. After the concrete is finished, the contractor makes sure that the access points are left visible so that the lid can be lifted up in case of emergency, as shown at these 4 points. With the concrete set for the lid, the final step is to put the casting on the cover.
For final acceptance, the water department and CM team must sign off on all inspections using this form.
And there you have it. I hope you gained something from this presentation. Special thanks goes out to anybody who helped make this presentation possible. Ed Yee, Bill Lau, Michael Wong, David Barajas, Steve Jackson, Gabriel Fernandez, and filming credit to Brandon Chan. Thank you for watching the AWSS training video. We hope you learned a lot. Now go out and inspect.
Thank
you.